Welcome back to the Deep Dive. Our mission, as always, is to take the really complex, really technical research that's moving the needle in machine learning and, well, distill it. We want to give you the critical knowledge you need to stay ahead.
And today we are really peering deep into the architecture of self-improvement for LLMs.
Right. Specifically, how they are bootstrapping their own planning and reasoning capabilities, how they turn themselves from, capable text generators into what look like expert strategists.
I think this is a profoundly important area because we're not just looking at a theoretical concept here. We're studying a mechanism, an accelerated one that the researchers are calling iterative deployment, or ID.
And it's already happening out there.
It's already fueling the development of frontier models. I mean, think about that feedback loop. It's continuous, it's high speed. A model gets deployed, users interact with it, successful outputs get generated.
And that data, the good stuff, gets scraped, curated, and then feeds the very next foundational model release.
Exactly. And this paper, it gives us the mathematical and the empirical framework to actually dissect that cycle.
Okay, so our source material today is the paper Iterative Deployment Improves Planning Skills in LLMs. It is mathematically dense, we should say that up front.
It is.
But the technical insights are just game-changing, especially for those of you out there architecting or even just selecting the next generation of AI agents.
So for our deep dive today, we have, I'd say, 3 core technical objectives. First, we have to meticulously understand the 4-step process of iterative deployment in a controlled setting. And it's far more sophisticated than just, simple data aggregation.
Okay, so the how. What's second?
Second, we have to rigorously validate the empirical claims. I mean, the performance gains they report are staggering. We're talking improvements in solved tasks, sometimes exceeding 400%.
400%. And then third, and this is maybe the most critical part,
I think
we need to analyze that theoretical finding, the one that mathematically connects this whole data curation and supervised fine-tuning technique directly to the foundational principles of reinforcement learning.
Right, because if the model is implicitly running a high-powered RL algorithm every time it gets retrained on user data, we really, really need to know what that implies.
For future architectures, for data management, for the stability of the whole training process. So our conversation is going to maintain a strict focus on these technical mechanisms and their practical implications for building reliable AI systems.
Okay, so let's unpack this core technical idea, iterative deployment, ID. At a very high level, it seems pretty straightforward.
Right.
Model A is out there, it produces successful outputs, we clean that data up, and we use it to train Model B. But the effectiveness, the reason this is so powerful, it seems to lie entirely in the structure of that training regime.
And in the precise technical steps of the curation. That's really where we need to focus our attention.
So how do they define it in the paper? So we define iterative deployment here as a training mechanism where the model is fine-tuned exclusively on its own valid outputs from previous generations.
So not on expensive, human-generated expert data.
Exactly. No human-in-the-loop, labor-intensive demonstrations. The current model, let's call it $, it acts as its own data generator. It's a process, sometimes called self-play or bootstrapping.
Okay.
The outputs it generates, or in the context of this paper, the successful planning task completions are collected. Then a multi-stage curation process kicks in and extracts only the valid and the high-quality traces.
And that curated self-generated data set is what's used for the supervised fine-tuning, the SFT, to produce the next model, plus the loop.
What's so fascinating here, and the paper is quick to point this out, is that this isn't some contrived lab setting. I mean, the authors cite historical precedent. They suggest that models like GPT-3.5 and others have sort of inherently been trained on successful outputs scraped after their predecessors were deployed. Right. The difference here is that this paper brings that mechanism into a controlled, measurable environment. And, this mechanism is only growing in relevance.
How so?
Well, as we shift from simple prompt and response to complex AI agent workflows, an agent doesn't just give you a final answer, it generates an explicit trace.
Right, the whole chain of thought, the actions it took.
The COT, the sequence of actions, any internal scratchpad reasoning, and the final result. And when those successful verified traces enter the public data stream or are collected by the model vendor, they just instantaneously become the implicit learning curriculum for the next big model release.
Okay, so let's drill down. Let's get into the weeds of a single iteration. The 4 technical phases that make this work, using Figure 1 from the paper as our guide.
All right. We start with phase 1, Deployment and trace collection. So the current model, an MLOR, which is just, a set of parameters, Sultan dollar, it gets challenged with a fixed external data set of tasks.
This external stimulus.
Exactly. The model then generates a trace, which we'll call Y dollar. And this trace is structured. It has to contain both the intermediate reasoning steps, the QT, and the final solution. This whole generation process follows the model's current policy, its probability distribution, TNYXI.
And that policy, TPKDSI, that's just the probability of any possible output given an input.
Yeah.
The goal of this whole ID process is to refine that distribution, right? To make it assign a higher probability to the good stuff, the successful, efficient traces.
Precisely. Which brings us to phase 2, validation.
The first crucial filter.
This is the mechanism that dictates success or failure. It's the implicit reward signal. So we introduce a deterministic external validator, VSY, which rigorously assesses that generated trace.
And for these planning tasks, the validator is a formal checker.
Yes, something like VAL, which is the standard tool used in the international planning competition. It verifies PDDL plans. And the validator is binary. It acts as a correction mechanism, or you can think of it as a proxy for an ideal user preference. It returns true, or a 1, only for valid, successful solutions.
And false, or a 0 otherwise.
Right. And the critical insight here is that all the invalid plans, and the paper notes this is often a huge majority of the outputs in early generations, they are immediately discarded.
Thrown out.
Gone. This hard cutoff is the first step in creating that high-quality learning signal.
So if the model generates 100 traces, and maybe 90 of them are junk, they just get thrown in the bin, we only move forward with the 10 successes, which takes us to phase 3, curation and aggregation.
Right, where we build the actual training set, 10 Ls plus 1.
Well, why isn't it enough to just dump the new successful data into the training set?
Because if you just aggregated all the valid traces, you dilute the signal. You could introduce conflicting or inefficient examples, which could lead to, policy degradation or even forgetting previous successes.
Anastrophic forgetting.
Potentially. So to prevent this, TLN plus 1 Poulin is built by aggregating the valid traces from the current generation, DI, with all valid traces from all previous generations. That's the big Bipwood val apart. This retention of prior successes is absolutely essential for robust, continuous learning.
But the really technical bit here is the second curation step, the selection mechanism. If the model, across all its generations, has found multiple ways to solve the same problem, we don't just keep them all. We apply some criteria.
Exactly. And the specific criteria they used reveal what they're trying to teach the model: efficiency and simplicity. So they prioritize, number 1, the shortest plan length.
Okay, so pure efficiency. The fewest steps to the goal.
It immediately promotes efficiency. It rewards the model for concise solutions over, rambling ones. And then number 2, if there's a tie-in plan length.
What then?
They break the tie by selecting the trace with the fewest reasoning tokens.
Okay, that second criterion is a really powerful technical directive. It's explicitly encouraging the model to internalize the logic. It's basically saying, look, don't just write a long, detailed explanation for the sake of it. If you can solve it concisely, that's better.
That's it, exactly. It's moving the model away from verbose chain-of-thought reasoning towards distilled, effective policy execution. We're building a preference for concise, effective reasoning that solves the problem efficiently.
And that brings us to the final step, phase 4, supervised fine-tuning.
Right. And this part is actually pretty standard. We take the prior model weights and we train the new model, 1 over plus 1, on that curated data set, tether better, using the standard next token prediction objective.
So the learning step itself is just regular SFT.
It is. But the data, that curated, self-generated, aggressively filtered success data set, that's what's unique.
Let's pause here for a neural signal check. The core hypothesis here is bootstrapping. Simple successes become the foundation for complex ones. Can you just elaborate on the significance of the model creating its own learning curriculum here?
Well, the mechanism is effectively a self-curating, difficulty adaptive learning program. I mean, you can think of it like a highly specialized form of knowledge distillation. The simple, short plans that Generation 1 manages to solve. They get rigorously verified, curated for maximum efficiency, and then they're locked into the training data set.
Like a technical building block library.
That's a great way to put it. So Generation 2 no longer needs to spend its resources figuring out those simple subtasks. That knowledge is now solidified in its weights. It can treat those successful 3-step subtasks as reliable components.
So it can now attempt 5-step or 7-step problem.
Exactly. And when it successfully solves those new, more complex traces are added to the library for generation 3.
The Sokoban example from the paper really illustrates this internal curriculum building.
It does. I mean, with the PS pace complete complexity of Sokoban, the paths to success are just exponentially hard to find. So if Generation 1 can only reliably solve, say, one-box tasks, the valid traces from those solutions are aggregated.
Okay.
Generation 2, having trained on those simple, successful traces, now has a refined policy. It might be capable of solving two-box problems that require totally new sequences of pushes.
Right.
Those new, more complex traces then feed Generation 3, allowing it to tackle even larger tasks.
So the model isn't just getting more data.
No, it's getting higher quality, increasingly challenging success data that it generated itself. This constant upward pressure on complexity is what drives the massive performance improvements we see in the empirical results.
That's a critical distinction. It's not just volume, it's quality combined with sequential complexity. It's like a self-optimizing complexity gradient built right into the training process. So we've laid out the architecture. Now let's turn to the results. To rigorously validate that this whole ID process actually improves sophisticated reasoning, the researchers needed a domain where success is, objectively verifiable.
Right. Classical planning.
Let's do a neural signal check. Planning domains. Why was this choice so essential for technical rigor?
Well, classical planning is defined by deterministic actions, a fully observable environment, and discrete states. The tasks are all defined using PDDL, the planning domain definition language.
And why PDDL?
Because the correctness of a generated plan can be verified precisely and automatically, they use established tools like VAL, which is the gold standard for verifying plans in these big planning competitions. So we remove all ambiguity. We're not relying on some subjective human judgment of quality. It either works or it doesn't.
Okay, so they tested the Quinn3 4B base model across 5 generations in 3 key benchmark domains. And each one tests a different dimension of planning difficulty. Let's characterize those domains because the differences in performance across them they're pretty revealing.
Okay, so first up, we have Blocksworld. This is the standard stacking puzzle. You rearrange blocks on a table to match a target configuration. Its complexity is manageable, it's polynomial.
So it tests sequential reasoning, but it doesn't really have dead-end traps.
Exactly. Then you have rovers. This domain introduces multi-agent coordination. You've got multiple robots on a simulated Mars. They're moving around, analyzing soil, taking images, and critically communicating results.
So this is testing resource management and coordination.
Right. It's still polynomial in complexity, but the practical difficulty is high because of the state space and the coordination requirements.
And then we get to the technical heavyweight.
Sokoban.
Pushing boxes in a grid.
Right. And what makes it so infamous is that the agent can only push, never pull, which means a single wrong move can push a box into a corner and create an irreversible dead-end state.
It's PS pace complete.
Which implies that the time to solve the problem can be exponentially long relative to the input size. So if the model can show significant sustained improvement here, it's confirming true policy generalization into these deep, nonlinear search spaces. It's not just getting better at simple polynomial tasks.
And the results, they were not subtle.
Yeah.
Looking at the quantitative performance after 5 generations, the improvement is just dramatic.
Yeah, if we look at the metric of solved tasks, the relative improvements are massive.
Mm-hmm.
Blocksworld saw an increase of 196%.
Okay.
Sokoban, despite its immense complexity, also managed a 196% increase. But the domain that truly just leaped forward was rovers.
What was the number there?
A stunning increase of 401% in solved tasks.
401%. A 401% increase in coordination capability from a model just training on its own curated successes.
Yeah.
That is a powerful validation.
It is.
I want to spend a moment on that divergence. Why do you think rovers, a polynomial task about coordination, improves so much more than Blocksworld, which is more sequential, or Sokoban, which is PS pace complete?
That's a great question. It suggests that the ID process, with its preference for short and efficient plans, that curation step we talked about, is exceptionally good at distilling coordination primitives.
What do you mean by that?
Well, in rovers, tasks often involve complementary actions. One robot moves to sample, another moves to transmit data. When the model successfully finds an optimal coordinated trace, that successful trace represents a high-leverage macro action in the policy space.
Ah, I see.
And because the ID mechanism aggressively aggregates and prioritizes these efficient multi-agent sequences, the policy just rapidly zeroes in on optimal coordination strategies. Blocksworld is more sequential, it offers fewer opportunities for that kind of leverage, and Sokoban is just fundamentally constrained by its exponential complexity. Even highly efficient traces are still just chipping away at a vast search space.
That really ties the empirical result directly back to the technical mechanism of curation. It's getting better where the short, efficient plan criteria can deliver the most leverage. Now, the sources also mention some fluctuation in the later generation.
Right, and we have to acknowledge that. It's minor variance. Even with a clear trend, you have stochasticity in generative inference. So generation 4 might solve 150 tasks, and generation 5 solves 148. That's just expected sampling noise.
So the key takeaway is the sustained massive uplift from the baseline.
Exactly. It proves the refinement of the underlying policy.
Okay, let's talk about the unanimous at 3 metric. This feels vital because it gets at policy robustness. It measures the number of tasks the model solves successfully across all 3 separate experimental runs.
Unanimous at 3 moves beyond just measuring peak capability to measuring policy consistency. I mean, solving a hard task once could be a lucky sample from the distribution, right? But solving it 3 times in a row demonstrates that the policy distribution has permanently shifted to favor that success, and the data confirms it. Later generations consistently get higher unanimous at 3 scores in all 3 domains.
So ID isn't just teaching the model new tricks.
No, it's increasing the reliability and robustness of the underlying policy. It's making the model a more trustworthy planner.
Okay, so next we have to address the critical question. Is the model just learning the syntax of PDDL? Is it just getting better at the language structure? Or is it achieving genuine out-of-distribution generalization?
Right, and this is where the plan length distribution data comes in. If the model was only learning syntax, we'd expect to see gains on, easy short horizon problems. But looking at the data in Figure 4 for Blocksworld and Sokoban, we see really strong evidence of deep generalization. The model is expanding its capacity for complexity.
So what do those distributions specifically show about the difficulty ceiling?
Okay, take Blocksworld. The base model, Generation 0, it mostly finds successful plans up to about 20 steps long. Its capability ceiling is pretty low.
Right. By Generation 5, however, the model is successfully finding numerous plans extending all the way up to 35 steps. That's solving tasks that are significantly outside the complexity envelope the base model could handle. And for the really hard Sokoban, we see a similar pattern. The model is pushing the boundary of the plan lengths it can successfully generate.
Which confirms the learned policy improvements generalize.
To problems with much longer required execution paths.
And in the rovers domain, the one with that huge 401% gain, the increase in longer plans is even more obvious.
It is. The last 3 generations find significantly more plans in that 10 to 30 step range. And crucially, Generation 5 shows the most pronounced outliers for the really, really long plans. These are the hardest instances in the dataset.
That's the definition of out-of-distribution generalization.
It is. The model learned simple rules, used them to solve simple tasks, curated those successes, and now it's applying that distilled policy to solve much harder, longer tasks it never successfully completed before. And that's the core takeaway for system architects. ID doesn't just polish the existing skill set, it expands the model's capacity for complexity. But now for the finding that's maybe the most counterintuitive and what really distinguishes ID from other RL studies, the reasoning token analysis.
This is a critical piece of the puzzle. In prior studies of explicit RL fine-tuning, especially for complex reasoning, researchers often see a significant increase in reasoning tokens.
The model becomes more verbose.
Yeah, it basically writes a longer internal monologue to solve harder problems.
But Figure 6 shows that in the ID process, the average number of reasoning tokens does not significantly increase.
Correct. For Blocksworld and Sokoban, the average length of the chain of thought actually slightly decreases from Gen 0 to Gen 5.
It goes down.
Slightly, yes. For rovers, it shows a slight increase, but overall, the difference is negligible compared to the performance gain. We achieved up to a 401% performance uplift without requiring the model to generate substantially more verbose internal reasoning.
That observation is incredibly powerful. If the model is suddenly 400% better at solving complex problems, but it's generating the same length of reasoning, that proves the improvement isn't just a surface-level behavioral change.
It suggests that the SFT process on the curated, efficient data is optimizing the internal representation.
The actual policy weights.
The weights themselves are becoming sharper, more efficient, more effective. It's learning what to do, distilling the necessary knowledge, rather than just relying on generating a detailed, verbose explanation of how it's going to do it.
It's policy distillation in action. The knowledge is becoming internalized. It's moving beyond the need for superficial Kati expansion.
And that efficiency in planning, which was captured by that second curation step fewest reasoning tokens, is being reflected directly in the model's internal policy distribution.
So we have the empirical proof. Iterative deployment works, and it distills efficient policy knowledge. Now we have to turn to the paper's core theoretical finding, the foundation for understanding why it works so robustly. The ID mechanism, relying only on SFT over these curated valid traces, is mathematically equivalent to a specific case of reinforcement learning.
This is the centerpiece of the paper for a technical audience. They formally prove that this method is mathematically equivalent to reinforce.
One of the foundational policy gradient RL algorithms.
Exactly. And to understand the gravity of this, we need to realize that the SFT process, which we traditionally view as, a maximum likelihood estimation task, is, under these specific curation constraints, actually performing policy gradient optimization, which is the whole goal of RL.
Okay, let's break down the formal argument. Let's start with proposition 1, which shows the equivalence between SFT on valid traces and reinforce when the reward is binary.
Let's do a neural signal check. Proposition 1. This proposition states that the update direction of the gradients for supervised fine-tuning using only the valid traces and the gradients for reinforce with a binary reward are identical.
They point in the same direction.
Precisely. So to see this, we first have to formalize that binary reward function. It's driven by our validator, yx. The reward is y equals y if the plan is valid, and y equals if it's invalid. Simple.
Okay. And in standard reinforce, the learning objective is designed to maximize the expected reward. We calculate the gradient by summing the log probabilities of the trace weighted by the reward.
Correct. The reinforced gradient estimate is approximately the sum of the reward times the gradient of the log probability of the trace. Because that reward is binary, any invalid trace where the reward is 0 contributes
Nothing.
0 to the entire sum. So we're only summing the contributions from the successful set of traces, which we'll call $+. The reinforce objective effectively just ignores all the failures.
Okay, now let's look at the SFT side of the equation. The SFT objective, LLSFT, is the negative log likelihood loss, and it's calculated only over that same set of valid traces.
The log, right. So the SFT loss is the negative sum of the log probabilities of the valid traces. When you differentiate that SFT loss, you get the negative sum of the log probabilities of those valid traces. Now you just compare the two.
So the gradient ascent step on the RL objective, which wants to maximize the reward, is mathematically identical up to a positive scaling factor to the gradient descent step on the SFT loss, which wants to minimize the negative log likelihood.
They are pushing the policy in the exact same direction.
Increase the probability of generating successful traces.
The update directions are identical. This is the technical confirmation that the simple act of filtering successful outputs and fine-tuning on them is performing policy gradient optimization. The curation mechanism, driven by that binary validator, it acts as a hidden implicit reward model.
Which simplifies the alignment problem a lot.
Immensely. It relies on observed success rather than a complex hand-engineered reward function.
But the real world is messy. You're rarely training only on data from the current model. When a developer scrapes the web, they get successful traces generated by older models, right? $M today, $2.
Which brings us to proposition 2. This introduces the necessity of using off-policy data traces generated by previous or behavior policies. Let's call them beta.
This is where the math gets more complex.
It does. And Proposition 2 provides the crucial technical bridge for continuous deployment. It proves that SFT on a mixture of on-policy from the current model and off-policy from the old model, valid traces, is equivalent to reinforce augmented by importance-weighted contributions from that behavior policy.
Okay, importance sampling. That's a technique from off-policy RL, like Q-learning. Why do we need it here?
We need it because the traces generated by the old model might be very improbable under the new refined policy. If you train your new policy on old, unlikely data without correcting for that difference, you're going to introduce massive variance and instability.
So importance sampling corrects for this.
It does. You calculate the importance ratio. The probability of the trace under the old policy divided by the probability under the new policy.
So we're weighting the success of the old model based on how likely the current model would have been to generate that same trace.
Precisely. If the old model found a trace that the new model already assigns a high probability to, the ratio is low. That trace contributes less to the update. It's less surprising, less valuable.
But if the old model found some rare success that the new model still thinks is highly improbable,
Then the ratio is high, and that trace is weighted more heavily, driving a strong gradient update. This ensures that those successful historical traces are incorporated into the current model's optimization in a stable and mathematically RL-consistent way.
so this means that every time a model developer scrapes a massive data set of successful, high-quality LLM outputs from various versions and then runs SFT on that data,
They are implicitly executing a powerful, importance-weighted, large-scale RL update step.
that is a profound technical implication. The community often views SFT and RL as totally distinct training stages. This proves that if the SFT data is curated based on a binary success criterion, they converge.
They do, which leads us to the implication for training regimes. The ID mechanism offers a potent alternative to explicit RL methods like PPO.
What's the efficiency advantage there compared to PPO?
The primary advantage is you get to circumvent the complexity of explicit reward model design and the inherent instability of on-policy RL algorithms like PPO, which require constant data regeneration. ID relies on a simple, robust binary signal. Did it work or did it fail?
And that signal comes from a deterministic external validator.
Right. For complex, open-ended reasoning tasks where designing a dense, continuous reward function is nearly impossible, ID just simplifies the optimization landscape. It guarantees a clear, high signal gradient without the architectural overhead of adversarial RL training or the complexity of managing KL divergence constraints, which PPO needs to stop the policy from wandering too far.
So if your task has a clear success criterion, ID provides a highly data-efficient, mathematically rigorous path to policy improvement that just bypasses all that PPO complexity.
Exactly. It decentralizes the reward model design to the external validator, or in the real world, to the revealed success preference of the user.
Okay, we've established the architecture and the mathematical link to RL. Now let's really focus on the practical difference maker, curation. We've touched on it, but we need to quantify how much that quality filtration step actually matters.
This is a great point. Let's do a neural signal check. Curation matters. The researchers did a crucial ablation study. They compared the Blocksworld experiment with and without that quality curation step, prioritizing the shortest plan and fewest reasoning tokens. And the results, detailed in Table 2, are technically stark.
Okay, let's compare the two paths. The non-curated version just kept all the valid traces it found. It still improved, right? The base model solved 52 tasks, and the non-curated Gen 5 solved about 79, a modest improvement.
Right. That minor improvement confirms that just having correct examples is better than nothing. But the model that underwent the full aggressive curation, Gen 5 of the curated version, reached 154 solved tasks.
That's nearly double the performance of the non-curated model.
The curated approach achieved a 94% improvement over the base model, compared to the non-curated version's much smaller gain. Curation is the difference between minor polishing and a fundamental policy leap.
And here's the part that is just a shocking technical efficiency win. To get to 154 solved tasks, the curated version used only 356 total training traces for its Generation 5.
Right.
By contrast, the non-curated version, which performed far worse, had to process 4,017 traces.
That's profound. Curation is not a luxury. It is crucial for maximizing technical performance while minimizing the required training data volume. It functions as an incredibly efficient form of policy distillation. It ensures the model is trained only on examples of optimal resource-efficient success.
It accelerates the convergence of the policy.
Dramatically. It makes ID a powerful tool for rapid skill injection.
And this efficiency gain, it naturally connects to a major technical concern facing LLMs. Model collapse. Other research has shown the LLMs trained recursively on their own synthetic output can degrade, they can lose capabilities because the data distribution shrinks and gets less diverse.
And the authors explicitly frame curation as a potential necessary mechanism to delay or even prevent that collapse. The key difference between the ID process and those theoretical collapse scenarios is that ID explicitly filters for valid traces. It maintains a continuous, high standard of quality.
So it's not just eating its own tail, so to speak.
Exactly. Now, they acknowledge that the long-term effects over hundreds of generations are unknown. but they didn't observe imminent signs of collapse up to 10 generations in the planning domain. This suggests that quality filter is a major divergence from the collapse assumptions because it prevents the policy from learning from its own low quality or noisy output.
It ensures the model is always learning from successful solutions, verified against an external standard.
Precisely.
Okay, now let's address the most critical technical implication for alignment and safety: the risk of uncontrolled gradient descent. We just established that ID is RL with an implicit reward function derived from indirect user curation.
This is the high-stakes technical challenge. In standard explicit RL for alignment, reward functions are meticulously designed. They encode safety constraints, desired human preferences. But in iterative deployment, the implicit reward function is opaque.
It's a black box.
It is. It's a function of the external validator, yes, but also of the revealed preference bias inherent in the successful traces that users choose to generate and validate. It is incredibly difficult to introspect or control this implicit function.
So in a real-world deployment, this implicit reward derived from general user preference, like a preference for speed or a certain tone, could just violently clash with the gradients from explicit safety training.
It's a fundamental gradient conflict. Imagine a model has been explicitly tuned via PPO to refuse specific tasks that could be misused. But then, the implicit reward function from benign user curation heavily optimizes for, say, maximum planning efficiency at all costs.
Or solve hard problems quickly.
Right. The ID process might then take massive, unpredictable gradient steps that directly oppose those intentional safety alignment efforts. The technical concern is that this opaque, implicit reward function could lead to large, uncontrolled gradient steps in the opposite direction to the safety gradients.
And the paper explicitly warns about this risk. If the ID process is basically policy optimization driven by an uncontrolled high-signal binary reward, understanding the resulting gradient vectors is crucial. You have to know what hidden biases that implicit reward function is maximizing.
Exactly. As these iteratively deployed AI systems become foundational, monitoring and managing the properties of these implicit reward functions becomes a top technical priority. If we can't measure the implicit reward, we can't effectively predict or debug shifts in model behavior caused by this continuous self-training.
This has been a really rigorous deep dive into the mechanisms driving self-improvement in LLMs. Let's try to synthesize the key technical takeaways from this research on iterative deployment.
Okay. First, iterative deployment is a rigorously proven mechanism for bootstrapping LLM planning skills. It achieves staggering empirical performance gains, up to 401% in that rover's domain, and provides powerful evidence of out-of-distribution generalization to harder, longer horizon problems.
Especially in complex domains like Sokoban. Second, the effectiveness of the ID mechanism relies entirely on its efficient four-step cycle, and that cycle is driven by aggressive, quality-based curation.
And that curation step, prioritizing the shortest and simplest valid plans, is crucial for efficiency. It delivers vastly superior policy updates with just a fraction of the data compared to non-curated training. This makes ID a powerful tool for accelerating skill acquisition.
And third, the process is mathematically proven to be a form of reinforcement learning. Specifically, supervised fine-tuning on valid curated traces is equivalent to policy gradient ascent to reinforce with a powerful, albeit implicit, binary reward signal.
And that signal is driven by data quality and importance-weighted contributions from previous model generations.
So the technical implication is clear. Foundation models are already learning from their own success in a high-powered, RL-like manner, driven by user preference and external filters, whether the developers explicitly intended it or not.
Which brings us back to our most intriguing technical observation. The models are becoming dramatically better planners without generating substantially longer chain-of-thought reasoning tokens.
Meaning ID successfully optimizes the internal representation of the planning knowledge. It makes the policy itself more efficient rather than just relying on verbose output.
The model has distilled the policy, which leads us to our final provocative technical thought. If the LLM is becoming its own highly effective teacher through this implicit RL loop, and it's prioritizing internal policy distillation over surface-level verbosity, the critical next step for technical accountability and governance is this. Can we reverse engineer the specific features or weights that the implicit reward function is truly maximizing?
So move beyond just the abstract concept of a valid trace.
Exactly. Can we pinpoint the exact change in the policy distribution that's being driven by user curation? We need to be able to monitor and control those gradient steps before they risk undermining intentional alignment efforts. We have to understand the geometry of the self-generated reward landscape.
It's the difference between knowing that the model is getting smarter and knowing the specific technical path it took to achieve that intelligence.
And that distinction is vital for stable deployment.
Indeed. Thank you for joining us for the deep dive. To stay updated on the latest in AI and ML concepts, visit our webpage, neuralintel.org, and check us out on YouTube. We'll see you next time.